Right.
Gotcha. Right. Mr. Haddock, lead on.
Right, so we're not going to be using anything too complicated in this. So you don't need to know much about the transmission of power other than the fact that if I put a lever on here, redstone out here, and a torch, just need to get a torch in the inventory, it's another important thing, then all you need to know is if you put a lever, block, redstone, if you pull the lever, the redstone comes on. So all logic gates, you can make them out of pistons, but I'm going to show you how they were originally designed to be made. All logic gates were originally designed using a redstone torch. This is a redstone torch, and it's attached to this block, and this redstone dust, you can see it goes into the block. So when the redstone dust comes on, it powers the block, and because the torch is attached to it, the torch turns off. What that means is the torch here is a NOT gate. If the input is 1, the output is 0. If the input is 0, the output is 1, like it is now. So if I hook up this redstone lamp, you can see it's turned on. If I flip the lever, power is on, redstone torch turns off, power is off here, and the redstone lamp is off.
So this is useful for a number of different things, isn't it? Having the ability to turn an input off.
Yes. But essentially, this means that every other gate can be made, because every other gate can be made of multiple NOT gates. This is what a NOT gate is. So I'll just turn that off and turn it on. Now, a useful purpose of NOT gates, a useful thing to know, and we'll come and use this later on, is, so I'm going to put a redstone, a lever here, some redstone down, the torch, and the torch is on. I'm going to put a redstone dust there, the torch is off. I'll put a bit more redstone dust, and the redstone lamp is off. The important thing to know, so here we've got 2 NOT gates, and now the lever, when I turn it on, the redstone lamp comes on. When I turn it off, the redstone lamp goes off. And that's because 2 NOT gates in series like this equals just a piece of wire.
Yep.
So if you've got 2 NOT gates in series like this, you can just simply get rid of the 2, put a bit of wire down. And we'll use this fact later on, so to have a look at some of the other redstone logic gates that we can
Question for you.
Go on.
Does a redstone lamp, in the configuration where you had the 2 redstone lamps, does a redstone lamp reset the power value back to its maximum again? So can you use it to range extend?
Torch, you mean?
Sorry, redstone torch. Does it reset the
Yes.
so it extends the range?
Yes, so here, this is a power of 15. So if you put a torch down, so you could essentially, before repeaters were in Minecraft, people used torches as repeaters. So as you can see, if I put this down and I go along here, the power decreases.
Which you can see because of the brightness. If you look at it, it's getting dimmer and dimmer.
Yeah, the brightness goes down. And if I put a torch here, so initially this will be off because it's a NOT gate, remember. Put a redstone lamp there. Put a bit of redstone there. C.
Ah, yes. So you're getting a maximum strength back over here again then. Okay. I just wanted to, because that seemed like a good way, because we've got repeaters now, but this seems like another way of doing it if you don't have repeaters.
Yes, so this is part of a discussion in transmission, which I might do next week. So the next so from that you can make the basic redstone gates. So the most basic one is what's known as an OR gate. So I'll just put a bit of wall down. I'm going to put a redstone lamp there. Redstone dust down like that. And a lever. So that's just your normal wire. But what I can do, I can hook up another wire here to another lever. And now this is an OR gate. And it's an OR gate because you need to turn either this lever on or this lever on. So it's called an OR because the operation is OR.
One or the other.
One or the other.
What happens if you put them both on?
If you put them both on, it both goes on.
Okay,
And
so
we'll talk about
It's a proper OR. It is a proper OR gate then.
It's a proper OR gate, and we'll get to the other type of gate that Matt's talking about later.
Okay.
But there is one thing you need to be very careful about this. Let's say I put another bit of redstone here, and I put a piston here. And let's say the logic is, I'm going to call the left A and the right lever B, that the redstone lamp comes on when I want A or B on, but I want the piston to only come on if B is on. So what you can see is A works correctly,
but B does exactly the same.
It pulls the piston, while B works correctly. So you can see if you pull A, I don't want the piston running. And that's because you get crosstalk. And what's happening is when you design this, you're thinking, ah yes, the redstone signal is going to come along here, turn left and round here and along here. And you forget that the redstone signal can also take this path.
Yeah.
And that's where you can use a repeater, so you can destroy this redstone dust and put a repeater there. Now B works just the same. And now A does not extend the repeater.
So the repeaters are directional then?
Yeah, so a repeater is essentially a diode.
A diode, yeah.
It allows power to only go in one direction, and that's a very useful piece.
Okay.
So, the other basic gate, I don't want to put a lever down, I want to put some redstone down, is an AND gate. Now there are various types of AND gates, but this is the most common and the basic one that's used all of the time. So, I'm going to put a redstone lamp there. Now I'm not going to describe exactly why this works now, because it requires a bit of explaining to do, but I will explain it later. So what this is an AND gate. It's again, you just remember the word AND. If you want the redstone lamp to come on, you need A and B on. So you turn both A on, just A on, the redstone lamp stays off. If you turn just B on, the redstone lamp turns off. If you put A and B, the redstone lamp comes on.
I see. That makes perfect sense.
And this is a very useful gate, the OR and the AND gate. You can make essentially any logic expression out of these.
Well, it's important to realise that they make computers out of these gates, isn't it?
Yes, yes. And the AND gate can be extended. All you do is you just put another torch down and extend the redstone dust a bit further. The only thing you've got to consider is that the furthest torch has got to be able to power this redstone torch down here. So you can now see that I now need A, B and C on for the redstone lamp to turn on.
Excellent.
So now we'll
good.
move on. So this is the OR AND gate. What happens if we want the output to do the opposite? So for that, what we're going to need is a NOR, a not OR, and a NAND, a not AND gate. This is where I've got to be careful what I say, because you can get the two confused. Hang on, I'll put that there first.
So you can actually already see that you've combined a NOT gate with your other with the OR gate there.
Yeah. So essentially, what I've done here is I've taken this OR gate over here. Notice the redstone repeater isn't there, and we'll get to that in a minute. And then all I've done is I've added on to the output of that this NOT gate.
You need to put a lamp there, don't you, or a torch?
So all I need to do is put a torch there, and the lamp comes on. And now what we want is that if A or B is on, the redstone lamp turns off. We want it the opposite of the OR. So A turns on, the redstone lamp turns off, turns on, and the redstone lamp turns off. And if A and B are on, the redstone lamp turns off. So this is A or knotted. So a not OR gate or a NOR gate.
Yep.
Now you may ask, why didn't I put the repeater there? Well, you'll see in this design that we still have the same problem. The piston extends when A is pulled. So one option is you can put a repeater here, but what you've got to remember about repeaters in torches is that they add delay to the signal. It takes longer for this redstone lamp to turn on, or turn off in this case. So if B turns on, it takes 1 tick plus 2 ticks, or 2/10 of a second, for this redstone lamp to turn off. But we can reduce that to 1 by moving the redstone torch to here. See now, we've essentially got 2 wires going into this block, which this redstone torch is attached to. You can see now we have that A turns off the redstone lamp but does not extend the piston, and B does extend the piston and turns off the redstone lamp.
So the key difference there is that the green wall square that's sticking up, while it is powered, it does not conduct power. It's only the torch that is conducting the power, which is why it does not then come out towards the camera, towards the piston, because the green wall is receiving power but not passing it on. So that's why you've got that difference.
You can imagine torches like power suckers. They suck the power out of the block, but redstone dust cannot suck the power out of the block, essentially.
Yeah.
So again, you can see we can make a NAND gate. But this time, you'll notice it's slightly different in that I'm not going to... hang on. Build that bit further up. I'm not going to add the redstone torch at the end. And if you remember, right at the beginning I said that you can cancel out 2 gates. So what that means is, so we can start with the AND gate. So that's our AND gate. Someone torch there. Dust lamp. So you might think, ah yes, that's our AND gate. If you remember all the way back here, these 2 redstone torches are in series, and therefore they can be cancelled out. Here we have 2 redstone torches in series, so we can get rid of the 2 redstone torches because they cancel each other out and just wire it up. And then if I pull the left one, then the redstone lamp comes on, because remember this is a NAND gate, so we want the redstone lamp to turn off when both inputs are on, both A and B. So with just the left on, it doesn't turn off. Just B on, it doesn't turn off. But if we put A and B on, then it does turn off. So therefore it is a NAND gate. And finally, there's 2 special gates. So I've got to remember how to build these, because these are a bit more complicated. And these are called the exclusive OR XOR gates. So I want to do that. What will happen is after the stream, I will put this somewhere and people can have a look at it, so that they can work out how they work and they can use it as a quick reference guide. Some dust on there. That there, and then I want 2 redstone dust here. Other input. So lever. Now if you remember back in the OR gate, back here, if I put both A and B on, redstone lamp stays on. There are some cases, and this is used in what are known as arithmetic logic units, which is a fundamental component of your CPU and your computer, where you actually want it to turn off if they are both on, but still turn on if one or the other is on. And this is what this gate does. It's the XOR gate. So you can see if I turn the left on, the redstone lamp turns on. If I turn the right on, the redstone lamp turns on. If I turn both on, the redstone lamp stays off.
Very good.
And so the best way to think
what
of
does the witch think?
I don't know what the witch thinks. Easily confused, can get rid of the witch. She's somewhere around here. So what's key to this is, if you look, this redstone dust goes into this block. Don't worry about the torch on the top, we'll talk about that in a minute. And it comes out at the bottom, over here into another redstone torch, so essentially these two cancel out, and it goes into this here, which looks a bit like an OR gate. So this is the OR gate, but remember, we want to deduct the AND gate, which is this case here, where we have two torches, join the dust together, and a redstone out. And that's what this is. What you can see is that the torches come up here, they join together here, and then they come into this torch. So what we essentially have is this here is the inverse or not of this input, and this here is the inverse or not of this input. So what we're essentially doing is, by using this torch, we are adding it to the inverse, or essentially deducting or taking away the AND case. So an XOR gate is simply an OR gate minus the AND gate. And then simply the final case that you don't know about is the XNOR gate, which is just the inverse of this. Just noticed that comment from C. Rogers. Okay, so we've done what we want if we want the inverse of the output. So you might want to ask, what happens if we want the inverse of the input? So we'll start with the OR gate, but we'll inverse the input first. So if you remember, this is our OR gate. We've got our two inputs here. But I'm going to invert the inputs first. I'm going to have the A and B. So I'm going to have. So you've got to remember, these are now the opposite. Oh look, easily confused is killing a witch. Right. So now, if we have inverse, we can see what happens when we do the inverse of it. So if I put. So this is now. Because I've turned it on, I've actually turned this torch off, and the redstone lamp stays on. If I turn this on, the redstone lamp stays on. But if I turn both on, the redstone lamp turns off. So this means that if we inverse the input and OR them, it produces exactly the same as this one, which is the NAND gate, if you remember correctly. And you can see that we've got these two torches, and then they join together into this OR gate. And here we've got these two torches, and they join together in this OR gate. So it means a NAND gate is just an OR gate with the inputs inverted. So you might ask, what happens if we invert the AND gate? So we will bring this down here. Here's our output. There is our AND gate. What I'm going to do is here, I'm going to invert the input, invert the input. So I can put the torch here and the torch here. If I turn this on, the input turns off. If I turn this on, the input turns off. If I turn both on, the input turns off. So this is essentially, although it's an AND gate where we've inversed the inputs, it's actually behaving like a NOR gate. And you can see that we've got these two torches in series. And over here we've got these two torches in series. So these two can cancel out and be removed. And then we just have the two inputs joining together like an OR gate and being inverted by this torch. Which looks just like this case, where we have these two and they're inverted by the torch. So an AND gate with the inputs inverted is a NOR gate. And finally, for completeness sake, what we can do, we can invert the inputs. So what I'm going to build here is a OR gate, but I am going to invert the input.
See you later,
then
PT.
invert the output. So there's our inverter to the output. Here's our OR gate. Here's our inverter to the input. There's our redstone bust. Put the torch on. If we turn the left one, the redstone lamp turns off. Turn the right one, the redstone lamp stays off. But if I put both on, the redstone lamp is on. So essentially this here is a NOR gate, but we've also inverted the inputs, and it's behaving exactly like a AND gate. You can see that here. So all you've got to remember our AND gate is you inverse the inputs, join the power together, inverse the output. It's the same here. Inverse the inputs, join them together, inverse the output. And then finally, funnily enough, you invert the input and then AND them together. Or invert the output as well. There's our invert of the output. Here it's our AND gate, so remember, invert the inputs, join them together, invert the outputs. Here we'll put the inverts of the inputs and then attach up the inputs. And lever on each one. And on the left one, and the left one and the redstone lamp comes on. Turn on the right one and the redstone lamp comes on. Turn on both and the redstone lamp comes on. So essentially this is an OR gate.
Yep.
And again you can see that through this cancelling out theorem. Remember, two torches in series, they cancel out. These two torches are in series, so they can cancel out, so we'll get rid of those. Replace it with dust. These two torches are in series, so they cancel out, and we'll replace it with dust. And these two torches are in series, we'll cancel it out and replace it with dust. And now it looks just like this order, except this one has this repeater in. And that is all the basic logic gates. So from this you can do a lot. Essentially anything that doesn't require memory is built with what you see here in front of you. It's all exactly the same.
So the foundations of what's controlling your computer right now are right here.
Yes. So from this you can build a CPU, or quite a lot of a CPU. You can't build the memory parts, we might do that in a later tutorial. But everything else you can build. You can build the fundamental components of how the food railway here. I think the only thing I haven't got here is a toggle latch and a SR latch.
Yeah, we've got various latches, clocks. There's all sorts of additional components we can bring in later on. But these are the fundamentals. And if you're looking at doing more stuff with Redstone, it would be worth your while practicing some of these. Haddock, are you going to put this somewhere so that people can sort of play with it and look over it? And
I won't put this one, but one next door, when I was practicing, if I fly over here, I was practicing in here and I've made a tidy one, and I will sign this up and we will put it somewhere. I haven't decided where.
Okay, so when we know where,
can play with it and they'll be able to look at it and use it as a quick reference guide, and they'll be able to essentially learn what all of these logic gates do.
There you go, folks. Well, I want to say thank you to Haddock for that. I think that was actually really nicely done. It's covered the basics of electronics engineering, because Redstone and electronics are not too far apart from each other. Yeah. One of the things I really like about Minecraft is Redstone suddenly elevates this thing to where you can create real machines with this system. It's really phenomenal. So thanks again, Haddock, for that. That was a really good tutorial.
Yeah, the Redstone's really important to me. I've had courses at university where I didn't really need to turn up to the lectures because I build Redstone and it's just exactly the same. In digital electronics, it's exactly the same. Everything's made out of inverters. You just invert the signals just like this, and it all works. Put diodes where you need them, and it works.
Excellent. Excellent.
If you
Right.
do this, you'll be good at electrical engineering.
Yeah, if you're learning at the moment, then you're at school or something, or you're just interested in electronics, you should really go as much as you can on learning Redstone and what you can do with Redstone, and it will help you in a very real and practical way. It's it's real. Also, what I'd say, this is not a game mechanic. Redstone behaves exactly like electronics, so you can actually use this knowledge practically in real life. Okay.